Good evening, everyone. Welcome to Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBC CPS IASC. It's my pleasure to introduce today's speaker, Dr. Ravishankar Krishnaswamy. He'll be speaking on a random walk from small world phenomena to web scale search. Dr. Krishnaswamy is a principal researcher at Microsoft Research India. He completed his PhD from Carnegie Mellon University in 2012 and was a Simons postdoctoral fellow at the CS department in Princeton University from 2012 to 2014. His recent research has been on designing new algorithms and data structures for very large scale vector search. He's also interested in approximation algorithms, especially for graph problems and clustering problems, and in studying models which incorporate uncertainty in the input, such as online algorithms and stochastic optimization. Over to you.
Thank you. Thanks for the invitation and thanks for joining the talk. So I'll be talking about vector search algorithms. It will be a pretty light talk in content, so feel free to interrupt anytime you have any questions. And you can go slowly over the topics also. Okay, so the first part of the talk, I'm just going to talk about some experiment that was done in the 60s by Stanley Milgram. He's a psychologist. He was a psychologist in Harvard University. So how many of you know about this experiment that Stanley Milgram did? If nobody knew, that's good because this can be one takeaway. If there's no other takeaway, this can be one takeaway from the talk. So what Stanley Milgram did is, you can read this thing. So he was trying to explain this often encountered phenomenon that we see in real world, where we meet somebody and then either we know that person directly, or we both know a mutual person, mutual acquaintance, and then we come to the realization that it's a small world, right? So we say Bangalore is a small world, Chennai is a small world. So world itself is a small world. So you can read this story here. So two strangers bumped into each other at some cafe, and then they discovered that they both know some common person, third person that's common to them. So he was trying to understand through psychology and through behavior, social networks, how is it the case that, like, there are billion people, 7 billion, 8 billion people in the world. How is it the case that we are also very well connected? Right? That's the question he was trying to study. I mean, each of us knows maybe like 200 people, but we very quickly we realize that we either know directly or we know people through mutual contacts.
Does it hold true always?
Doesn't hold true always. So what do you mean though?
Like, okay, I know 100 people, you know 100 people. There might be instances like these 100 people didn't meet your 100.
Correct. So what he observed is not that it's either direct or one hop. He observed that up to 5-6 hops, you can find out the connections. So I might know somebody, person X, who might know Y, who might know Z, who might know you.
Correct, but that also might break. I mean, that doesn't hold to always.
True. Yeah. I mean, yeah, I could just be alone in the whole world and not know anybody, right? Yeah. So the question he was trying to study is, how is it that any two people in the world are linked through short paths? And more importantly, he was trying to understand how can they discover each other. So it's not just that the fact that there exists a path between two people in the world, they are also able to discover these mutual connections quite easily. I will get into the details soon. And this experiment led to this result. This notion that everybody in the world is separated within 6 degrees of separation. Okay, so that's the summary of his experiment. So what did he do? So what he did is only in the US. So it's not a whole world, it's only in the US. So he started with a random person in Nebraska, some part of the US. And he told that random person, this is in the 1960s, by the way, no email, no like all these WhatsApp and all that, right? He told this random person, here is a destination, target, who's a stockbroker in Boston. So he gave this person some details about the destination. So who the recipient is, and what's the profession of the recipient, and what's the address, what's some details, right? Some basic details about the recipient. And this was the goal. So the source person had to send a mail, a correspondence to the recipient. But the constraint is the following: the sender is given all the information about the recipient, but he should only forward the letter to some person he knows, and he should forward it to the person he thinks is closest to the recipient. Right? So I have 100 contacts. I should think about which of these 100 contacts would know the recipient, would be closest to the recipient, would be most likely to be able to transmit the letter to the recipient. I should forward the letter to that person. And then that person should apply the same rule. So he knows the target person, Boston, name, address, and all that. But the constraint is he can't directly send the mail to the recipient. He should only be able to send it to somebody he knows from his contact list, right? And then the question is, I mean, this chain can keep progressing, but when the chain reaches this person in Boston, he would send the whole letter chain back to this Stanley Milgram, and then he would collect data about how long it took for the mail correspondence to reach the recipient. Okay, so is the setup of the experiment very clear? Any questions about the setup? So what he found was that, I mean, of course, there were several cases where the mail just reached a dead end. So I mean, some person received the mail and then said, hey, I don't know, I don't think any of my friends would know this person at all. And then it reached a dead end. So he discarded all the dead ends. Among the ones that actually reached the destination correctly, he observed that the average length of this correspondence chain is only 5.2. And that leads to this phenomenon called 6 degrees of separation. Okay, so that's the observation he made. The other thing you can see here, right? So I don't know anything about the target. The only thing I do is a very decentralized routing. So I look at all my contacts and I think who among my contacts will be most likely to reach the target. And I only look at this, I look at 100 neighbors and see which one is most likely to transmit the letter to the destination, and I send it to that destination. So I don't need to know anything about the global, like 300 million people in the US. I only need to make a choice among my 100 contacts. I forward the letter to one of the 100 contacts. They forward it to one of their 100 contacts and so on. So it's a very decentralized routing, which can actually show that you can send a letter from any start node to any destination node, right? And that's the nice part of this experiment. Of course, if you knew the whole graph, like 300 million graph, 300, like 100 or 200 contacts per node, you can find a shortest path algorithm, and there will exist a path from, if it's a connected graph, there will exist a path from any source to any destination, right? But that's a centralized algorithm. This one is a very decentralized algorithm. It says I don't need to know the whole graph. I can just make local decisions and still reach the destination quickly, efficiently. So that's the summary of this experiment. So any questions about the experiment, the finding? So if there's one takeaway from the talk, it's that the world is the 6 degrees of separation. So there is, that's Milgram's experiment from the 60s. So here is one example from his paper. So from the start, so he was tracking progress by distance to the destination. So from Nebraska to Boston, there's like 1,300 miles. Then the first person sent it to a contact who's only 700 miles away, then 300 miles away. But you can see it very quickly reaches maybe Massachusetts, and then inside that you make people don't know who among their contacts might know the destination recipient the most. So they make a lot of hops spent getting probably within the city of Boston or something. I don't know. So that's the observation he made. And so probably this hop is maybe either a relative or somebody who he thought was working in the field of stock trading, right? So those are the sort of decisions that each person would use. They would either send it to somebody who they know in closer geographically, or closer work-wise, or closer through some other like information, but not much information is known about the recipient. Okay, so now let's move all the way to the late 90s, early 2000s. John Kleinberg, who's in Cornell, was trying to understand how do we model such behavior. So how do we model human social networks where this sort of decentralized routing is able to go from the source to the destination. So he's trying to understand what kind of graphs admit such decentralized routing. Not all graphs will admit decentralized routing, right? If you have like a random graph, for example, decentralized routing will not work. So what he did is he was trying to model the US population. What kind of network connections do they have? What kind of friendships do they have? Social networks do they have? So let's take a very toy abstraction. This was the abstraction in his paper. So each person in the US is a point on this grid. It's an n cross n grid. So America is like a rectangle. So let's think of an n cross n grid. Each person is a node in this grid, and the representation of the person is just the x and the y coordinates. Okay, so that's the node. And there are two types of connections. One is just like neighborhood connections. I am connected to the person on the 4 lattice directions. And then this alone is actually a reasonable graph where you can actually use this sort of decentralized routing to go from anywhere to anywhere, but it will take a long path. You can't reach in 6 hops. You might, if there's an n cross n graph, you will take 2n hops to reach up to 2n hops to reach from here to here. Decentralized using just the coordinates works, but it's not great. It's very slow. So what he showed is you can actually add some long range edges. With one long range edge per node is enough. So you cleverly choose one long range edge per node, where each node will sample one of the other nodes to draw an edge, but that probability is not a uniform distribution. It's inversely proportional to the square of the distance between the two nodes. If there's a point here and a point here, measure the distance between these two nodes, take the square of the distance, and sample from a distribution which is the inverse square of distances. Okay, so nearby nodes are likely to have an edge, far away nodes are less likely to have an edge, very far away nodes are even less likely to have an edge. But it's this very carefully chosen 1 by d squared type of distribution. Is this setup clear? So on this, one long range. Each person chooses one long range contact. No, they will just sample from this distribution. So this distribution says what's the probability to have an edge here, everybody, right? So it's a discrete distribution over n squared minus 1 other points. You sample once from the distribution and draw that edge. Correct. So incoming I might have multiple, outgoing is one. Yeah. Yes. Yes. It's a directed. Yeah. So with this distribution, John Kleinberg was able to show that the greedy routing algorithm, without this long range edge, what could take up to n hops, now converges in log squared n hops. Okay, so he shows that just adding one edge per person brings this connectivity graph. Graph makes it much better connected. The other observation he had is that if your sampling probability is different, instead of inverse square, this r is a parameter. If instead of inverse square, if you do r less than 2, that means what? You favor you favor longer range edges, right? So that makes the graph too random. Then the convergence is not true anymore. If r is more than 2, that means you favor short range edges more. So again, that makes it too local. Again, it doesn't work. So for the grid, r equal to 2 is the right answer. So the routing here means that there is let's say there's a letter that's starting here, and then you want to transmit the letter to this destination, but the letter can only use local information to send it to the destination. Greedy routing means which among these nodes, which among my contacts will be closest, do I think is closest to the destination.
Random one, right? And that hopefully that will take you quickly to the right edge, right? That's what
Come again, I didn't follow that. So
you are sampling a neighbor from a distribution, right?
So I have like this node has 4 neighbors, and it is picking one random friend from this graph. Yeah. No, the source and the target are given to you, right? So I am telling you, once each person will be allowed to pick one random friend. So once everybody picks their random friend, then I will tell you, hey, you send a letter to this person. How quickly can you send it? That is just building the graph. Yeah.
Regularity, but I have one
Correct.
edge.
Correct. And just regularity is not enough, because if without this random edge, the path will take very long. Will just be which of my neighbors is closest to the target in terms of Euclidean distance or XY distance, right? Manhattan distance. So that's, but this was all a way to model the real world experiment that Stanley Milgram did, where letters are actually being sent very quickly. So yeah, this was a toy model. So this is the setup. He showed that this is the right distribution. So if you sample one random edge in this distribution, things work out very well. And the takeaway from this is that real networks are perhaps like human social networks are perhaps navigable, because they are able to nicely balance local contacts with these cleverly sampled long range contacts. So there's some little bit of randomness, there's a little bit of locality. The two put together makes them very nicely navigable. This greedy routing itself works very well. So in this grid example, just 4 nearby contacts and 1 long range edge is enough. So that's the result he showed. So I'll very quickly show why this proof works out, right? It's a
One big hop, and then after that it's all local.
No, the other person could also make a big hop. Yeah.
Typical paths.
I see.
Is it
typical in the real world experiment, is it? In no, you would make quite a few long range with this. Yeah.
So basically, how many is it mostly long range?
It will be mostly long range. Yeah, only like this. So it will be long, 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 then like a few short at the end. Yeah, correct. I did do some simulations. I didn't attach those plots here, so it's.
What does it say? Order counts.
Yeah.
So you saying you go back to log square, right? So in this, log n of them are long range or log n?
I don't. No, good. There are. I mean, John did a full, very thorough investigation, so the results are known.
Long edge is shorter, is in the right quadrant. So I have 1/4 the time take the long edge, and 3/4 the time take a short one.
Yeah, I'll show you almost a proof of that kind, but that would all go into this big O notation. So 4 versus, yeah, you're right. So I will show you, you're on the right track. I will show you the intuition for why this distribution is the right distribution. So let's say this is the source node and this is the target node. This is like the furthest apart pair, right? So it's the, and how long does this greedy routing take from to send a letter from this person to that person? So now suppose their distance here is some d. I mean, this is a general argument that works for any pair of points at a distance d. Let's look at a ball of like distance radius d over 2 around the target. Because this is a grid, there are roughly, I'm hiding constants all over the place here. There are roughly d squared points inside this grid. Area of that circle is like d squared, order of d squared. So there are d squared points in this grid. And now notice that each of this source is sampling an edge to any point here with probability proportional to 1 by d squared, right? So if you work out the math carefully, you will see that with constant probability, u actually has an edge to somebody in this ball. We don't know who, but somebody in that ball. And that person, and because u makes a greedy routing, you can, with that constant probability, you can make progress. He can reduce the distance to the target by at least a factor of half, by at least a factor of 2 with 1 hop, with probability constant, which is sort of what I'm saying.
This tells you that R actually depends on dimension. R is 2 is just perfect.
Exactly. For a 3D lattice, you would need RS3. Exactly. Yeah. But this, I think he was modeling people on the world, so he was looking at R is equal to 2. Exactly. Yeah. So that's why you expect convergence in log steps. And this is a proof sketch. To get the real proof, you need to work out a little more. You'll get log square. Okay. So this is John's modeling of Milgram's experiment. Okay, now we'll come to why all of this is connected to vector search and vector search algorithms. So that's the last part of the talk. So I'll motivate. Any questions until now? Okay, so one thing I'll tell you. So I'm trying out AI tools a lot lately. So most of the slides here are done by PowerPoint's AI assistant. So it decides what animation to use, what graphic to use. So see, I don't know what the LLM thought, right? So it could have decided. So like the title slide, let me. This one AI chose the background. Title slides, the title phrase and the title background AI chose. So a lot of things AI chose in this talk. So I don't know if I'm proud or ashamed of that, but okay. So let's look at this thing, right? Let's come to vector search. So now I'll tell you the motivation of the problem and then talk about the problem itself. So if you go do any type of search or retrieval on the internet, is it whether Google search, Bing search, ad recommendation, search in your email, do a search in ChatGPT, search in Amazon, Netflix, any of these applications, the core algorithm that powers all of this search is called a vector search. So I'll briefly explain what the vector search algorithm is. And this came about because of the emergence of deep learning and LLMs and all that. So the way modern day search and retrieval works is, whatever corpus you're trying to search over, like if it's Amazon, then all the products that Amazon has. If it's YouTube, then all the videos that YouTube has, right? Then there are trillions of videos in YouTube. So all of them, the video content is passed through some sort of language model or LLM or deep learning network, and it gets converted to a vector in very high dimensions. So the input to a vector search problem is a collection of n vectors. N itself could be into the order of trillions in extremely high dimensional space. So not 2 or 3, but think of thousands. So you have a billion or a trillion vectors in 1000 dimensional space. And these vectors all correspond to real objects, videos or websites or any of these things. And the goal is we want to maintain some sort of a data structure such that when the user types in a query, when I type in some text in YouTube, that also goes through a deep learning network and becomes a vector in the same d-dimensional space. The goal is we want to maintain an efficient data structure such that for this query, I am very quickly able to identify the closest vectors in this high dimensional Euclidean space. So once I do that, the magic of the way these embeddings work is that these 5 closest vectors happen to be the most relevant videos for my query, or they happen to be the most relevant websites for my query. Okay. Problem clear? Question? I haven't come to that yet. So the goal for vector search doesn't have to do anything to do with graphs, but I am going to describe a solution methodology that goes through graphs. All the vectors that, so you take in all the web videos or web pages, pass them through some deep learning network. For each video, there is one vector that gets spit out as a representation. Yeah, and the query, when the user types in a query, the same deep learning model gives me a vector, and I want to find the 5 closest vectors to the query, for which we are going to create an index. The user query. That is also vectorized. Correct. Exactly. It will be a text. So that is out of scope for our problem. The embedding model has to take care of mapping the text to the images and all that. That's the intelligence of the way the embedding model is generated. Yeah, all dimensions. So these are 1000 dimensional vectors. The distance between two vectors is just standard Euclidean distance between this green dot and the red dot. And I want to pick the 5 which are closest to the green dot. Say that again.
You have engagement algorithm for website. So why can't you use the same thing there? Like why do you need to take vector search algorithms or approximate nearest neighbor? Is it because you're considering even larger dimensions, or the input space is very large, like 10 trillion?
So how does PageRank work? Because PageRank, I'm not. And the other thing is, I'm not sure how PageRank adapts to the user query, right? It's a way to sort of prioritize rank pages based on how important they are, but it has nothing to do with the query, right?
We try to find somehow highest probability page. Right?
Correct.
Here you need to find the conditional highly probability page.
Correct.
And the conditioning event is what my query is, right?
Correct.
Somehow.
Correct.
So this question has some merit.
Absolutely. But PageRank alone, the basic PageRank, as I understand, has nothing to do with the query. It's a way of telling which page is more important than which other page based on how many links there are incoming. Right? Correct. So first, correct. So there you do, using the keywords, you first identify from, if there are a billion or a trillion websites, right? You identify the top, say 10,000 or 100,000 using keywords, and then do PageRank on those 10,000. The same thing you would do here. You would identify the first 100,000 using vector search, and then do PageRank on them for finalizing the ranking. That is correct. That is correct.
Trying to find the starting point. That will give you the good condition, but the starting point is exactly what you are doing. I need where to start.
Right.
And when you start, your water piece of condition. Right?
Yeah. So the way web scale search engines are developed is there are 2 phases. One is like a filter, which boils down, say, 100 billion into much more manageable 10,000. The other is much more complicated layer, which can do lots of more heavy machinery like PageRank and get you the top 100 to show. So think of this as the first step, which is like a funnel, which gets you down from, in reality, it's not 5, they will ask for 1,000 or 10,000. Yeah. So how would we build a data structure? So that's the real question that the rest of the talk is going to focus about. Okay. I'm going to start slowly work my way towards, I will eventually show you how to build a graph over all these points, but we will slowly work our way towards the graph construction. So what if the dimensionality of the point is not 100 or 1000, but if it's only 1, right? These points are all like just points on a line. Then I can build a very good graph for these sort of points, right? So, and suppose the query is here, I want to somehow quickly find out that this is the nearest neighbor to that query. And there are many methods here. So you could just do binary search. So it's very simple data structure, order and space, order, log, and query time. So if the points are all one dimensional, right answer to do is right thing to do is binary search. There is no need to do anything fancy. Suppose they are two dimensional objects. What you would do is, there are very nice algorithms even for two dimensional objects. You can, I mean, binary search works because there is a very clear ordering of these points. So because it's one dimension. In 2D there is no ordering, but the way we can do it is we can still construct so-called, there's a nice geometry idea called Voronoi partitioning. So we can find out a Voronoi partitioning of the space, and then we'll do two binary searches in some sense. So we'll try to first identify which, we'll divide the x-axis into many slivers, and we'll identify which sliver the query falls into. And then once you go into a sliver, there is an ordering of the points inside the sliver. So we'll then do a binary search to find out which the right nearest neighbor is inside a sliver. So we'll run two binary searches. So we have to do a lot of work to construct such a data structure. We have to compute this Voronoi partitioning and then intersect each sliver with the Voronoi partitioning and then maintain the ordering inside that Voronoi partitioning. It's a lot of work. So it's just a theoretical result. It's not a practical result. So the search time algorithm now does binary search in x-axis, then binary search in y-axis. But the number of slivers now, like your data structure complexity has gone up. It's not just one like a binary search. So even now it's okay, it's order and space and order, log, and query time. But this algorithm, Voronoi type of algorithm, when the dimensionality increases, the search complexity behaves very, very well, but the index complexity grows exponential in D. So it's order of n to the D. So it's not very good, it's not practical at all. The other extreme is of course the brute force, where I don't do any data structure. When the query comes, I just compute the distance to all the vectors and pick the top k. So that has very good space complexity. Query time is very bad because it's order ND distance comparisons and it's very bad. So in practice, this is completely ruled out. And this is also more or less ruled out because, I mean, if you do the math, just computing, I mean, using the flops argument and all that, right? Like if you compute distances of billion vectors in 1000 dimensions, it will run into minutes. And web scale is hundreds of billions. So you type in a search and maybe tomorrow, day after, search result comes. Then that's the way brute force will operate. So we really need algorithms that are much faster query time, but also don't have so much space. Don't, like, the space is much more manageable, and that's where we'll work towards. Okay. Any questions? Okay. So there are, again, this problem is very well studied in theories. There are results that show that if you want to actually get the top k nearest neighbors for all queries, it's practically impossible. So you can't do have algorithms that are polynomial space and sublinear query time. So you cannot do that. So we'll have to settle for approximate retrieval, meaning I won't get the exact top k, maybe I'll get 90% of the top k right, or something along those lines. So there's a notion of approximation that we deal with. Okay, so that's what we are going to go for. Okay, so now that we are motivated this goal of retrieval and also shown the complexity of like this high dimensional vector search, let me just rephrase the problem. So given a query vector, we want to identify the nearest neighbors, the nearest vectors quickly and efficiently. So that's the question. Definitely it helps. But that's not the focus of this talk. We can talk about this offline. It helps, but to an extent. Again, it shows that you can reduce the dimension to order of log n by epsilon squared dimensions. So if you put in the order and the epsilon square, it will come back to 1000. 3000 may come back to 1000. So it doesn't solve the problem entirely for us. We still need a good data structure to handle this problem. Okay. So now that the first two parts of the talk, we have shown how there are nice real world graphs that are able to decentralize in a decentralized manner, find out the target region very quickly, right? So we want to use that machinery for this problem. So can we build good graphs over these vectors such that this decentralized greedy routing is very quickly able to converge to the nearest neighbors of that query point? Because that's the whole motivation of this line of attack. Okay, so in Kleinberg's model, what's the difference between the first two parts of the talk and the third part? In Kleinberg's model, we are able to model both the nodes in the graph as well as the edges in the graph. Because these are all points on the lattice, the edges we were able to very carefully handcraft the edges and say greedy routing works well. Here, the vectors are given to us. Vectors are embeddings of high dimensional embeddings of videos or websites. So the nodes in the graph we have no control over. We only have control over the edges in the graph. What edges can we place so that greedy routing converges very well? So that's the real question that we are going after here. Okay. And just to show some example, these are some two-dimensional embeddings that I randomly generated and a graph I randomly constructed using our method. So just to illustrate what kind of what we are shooting for, right? So we want to build a graph where every embedding, every vector is associated with one node in the graph, and the graph should have small degrees. So the out degree of the graph should be somewhat reasonable, such that if there is any query, remember the query is not part of the graph, right? Query is the embedding of some text that the user types in, so it's not part of the graph. For any user query, if I start at this starting node and run a greedy algorithm, meaning this start node scans its 5 or 6 neighbors here, identifies which neighbor has the vector closest to the query vector. So it looks at all the 5 neighbors, each of them is corresponding to one vector. You compute the vector distance to the query vector and pick the one that's closest to the query vector. And then you iteratively walk in this decentralized manner, right? So if you keep iterating, what kind of graph will converge to the nearest neighbor and also converge quickly to the nearest neighbor? So that's the real question. Yes, correct. Out edges. There could be multiple neighbors, so 100 neighbors, let's say. Correct. That's true. And then a decentralized algorithm will quickly converge. Correct. Embeddings of the objects. That's it. Okay, so that's the high level approach. So I mean, we didn't invent this approach. We're building on a series of works. So I'm being a little unfaithful to the past work by just focusing on the concept. But the concept is the same across even the prior works. Okay, so how do we build such a graph? Let's revisit the one-dimensional example where we know that binary search works well, but can we still build a graph to simulate this binary search kind of concept, right? So here is a bad graph where this greedy decentralized routing does not work. Okay, so if the query is here, I start from my source, I go to P9, and then P9 has 2 neighbors, P1 and P11. Both of them are further than P9, so the search stops here. Right? So, and you don't converge to the nearest neighbor, which is one of P6 or P7. So this is a bad graph, doesn't work well, and this is like a random graph that I constructed. So random graphs don't work well for this reason. Okay, so random graphs will have short paths, but not through greedy routing. So here is a good graph, but not the best graph. So I just draw a line graph. Now I know that if I greedily route, I will, like the grid graph that I showed up front, greedy routing will work, but it could take order n hops. Okay. So here is a better graph, which is still very low degree, but can converge also very fast. So it's like this, slightly cleverer long range edges. So I have these 1 hop edges, then I have every 2 hop edges, 4 hop edges, 8 hop edges, and so on, which more or less simulates binary search. Okay, so if your query is here, you'll do one long range and then you will converge to the right answer. So the real question is, okay, if data is not so nicely structured, how can we build good graphs for real world vectors, which sort of capture this behavior? So I'm now going to present our algorithm that constructs the graph that we use for vector search. Okay. So each vertex, there are n vectors, each vector corresponds to a vertex. Each vertex is going to decide the out neighbors independently. Okay, you do this process independently for all the n points, and the result of that will be the graph that we get. So you sort the other points in increasing order of distance from this point. So P is the current point that we are focusing on. P is going to sort the other points in the data set in increasing order of distance from P. So in this case, it's just ordered by this V1, V2, V3, and so on. So P will definitely add an edge to the nearest neighbor, that the candidate V1. So P adds an edge to the nearest neighbor. What are the other edges P adds is what we are going to figure out now. So we loop through the other points and then we check, is there a point which is somewhat close to V1? If so, we skip that. P does not add an edge to that other point. Okay, so that's the rule here. So we are going to, when we add an edge, we are going to see who are the other points that can actually be blocked or that we can avoid adding edges to. That's the aim of this whole procedure. Basically, we are saying, are there points subsequent in this ordering whose, I mean, this is the exact rule, right? So is there a point such that I mean, I'll show it in illustration actually. So is this rule clear or should I do I explain? Do I have to explain a little more? Yeah. Yeah. So every point will decide its edges independently. So let's now focus on one point and see what edges that point has to choose. Yes. This is the index construction phase. So this is all a one-time cost. So yeah, so then I didn't explain that part very clearly. So the second point, the next point I'm going to see is, I want to see if an edge to V2 is necessary or not. Okay. Exactly. So close is very relative. I'll get to that. So when I want to consider whether I want to add an edge to V2 or not, I will look at the distance from P to V2, and then I will draw a ball of radius half around V2. And if I already have an edge to somebody in that half the radius ball, then I don't add an edge to V2. That's the rule. Then I look at V3. If I draw a distance of half the radius around V3. If there's already an edge to somebody, then I don't add an edge to V3. This rule is what I iteratively apply. I've written it in a slightly different manner, so that's why I'm struggling to explain. But the motivation for this rule comes exactly from that way back proof, right? Because the edges were added with probability inversely proportional, just so that you cancel out, you find somebody in that half ball. So we just take that rule, abstract it out into an arbitrary data set and say you apply the same rule here. Even if there's no structure, so what? We make it a deterministic condition for adding an edge. So in this case, V1 gets an edge. V2 also gets an edge because there is no edge in the half ball around V2. If you look at V3, again, you will get an edge.
Every node in some distance falls, so that I reach there and then I will
Exactly.
the neighbors there.
Exactly. We have tried to sort of see what Kleinberg's proof is doing and make it a more deterministic rule as opposed to a data dependent distribution. So now if you look at V4, right, if you draw a ball of radius half this distance around V4, V3 is already present. So we will not add an edge to V4. That's the rule. So it's sort of, you can think of it as a deterministic rule capturing that Kleinberg. So V3 that's V3's responsibility when it's choosing the edges. Yeah. Correct. Yeah. Because the algorithm is doing the same rule for everybody. So V3 will apply the same logic when it's trying to figure out its neighbors. It's very expensive. It's n cubed or something. Very expensive. So we have heuristics to speed it up. N cubed is not going to, it will take many years to build a graph. So it's not realistic. We have heuristics to speed it up. This is just a theoretically robust version that I'm presenting. Correct. That is very tailored to the grid points. This is a more robust graph which can work for any set of vectors. Exactly. V6 you add an edge. V7 you don't because V3 blocks it again. Correct. Yeah. Correct. Yeah. No. The motivation for when to add an edge and when not to add an edge comes from the proof of why that worked. The proof of why that worked was essentially, the gist of the proof was saying, as long as we ensure that U has an edge to somebody in this ball, the entire proof will work. The exact distribution was just a way to ensure that property in that data set. We are capturing that property and saying, let's apply the property to any data set. Exactly. So, and the proof, you guys already got the proof, right? So if the query point is some point here and this is the nearest neighbor of the query point, either S already has an edge to P, in which case you're golden, in one step you converge to the nearest neighbor, or S has somebody who has made progress towards the region of the query. So you will converge in log many steps. That's the real intuition for why this sort of graph works. So one thing I did not talk about is how big is the degree of this graph. It could be that there are data sets where the degree of this graph is very large, but in real world we see that the degree is very, very tolerable. So even if there are billion points, the degree is only like 100, few hundreds. So that's why this thing works out well. So okay, so we didn't have, in our paper we didn't have actual formal guarantees. There was a follow-up paper from MIT folks who actually showed that our graph has nice theoretical guarantees. So if the underlying metric has low doubling dimension, the degree of the graph is actually provably bounded, and the greedy search converges very quickly to a very nice approximation of the nearest neighbor. So if your true distance to the nearest neighbor is r, this algorithm will converge to something like alpha plus 1 by alpha minus 1. Alpha is some parameter here, I didn't. Alpha is this, how much of a ball do you pick? The 2 ball, right? That is the alpha parameter. Yeah, and we ran a lot of empirical experiments and showed that even for billion point data sets, you can actually compute the nearest neighbor with 3 milliseconds, 4 milliseconds. We only end up doing like 50,000 distance comparisons for a billion points, as opposed to brute force, which would do 1 billion distance comparisons. And the latency is sufficiently small, like a few minutes has come down to few milliseconds, which is very, very tolerable and accepted in practice. So this algorithm is used a lot in, extensively in Microsoft, and also a lot of other outside people use this algorithm, so for their products. So that's pretty much all I wanted to talk about. Vector search is a very hot area, so if you guys are interested, there's a lot of opportunity in this space, and happy to collaborate. What does Google have? They have their proprietary vector search algorithm. They have released one version of it, which is a combination of a tree and a graph. We go with purely graphs. They go with a combination of a tree data structure and a graph data structure. A lot of the ideas are similar, and the nice thing is, our algorithm has come out as a paper. The code is open source. Google does similar things, so there's a lot of cross collaboration across industry happening here. Correct. Yeah, we have tried. Yeah, there is possible. We have tried some optimizations. Doesn't help too much, and conceptually it's 3 steps, and we always cache like a lot of things in memory and so on. So things work. There are systems tricks to do to overcome these issues. Yeah, so that's pretty much all I wanted to cover. So. Any search and retrieval recommendation requires this. So YouTube, Amazon. One could do it, right? Because there was a team in Aadhaar which came to us to talk about how they use vector search inside their thing to certify closeness. So sometime last year, maybe. That conversation didn't proceed too far, but okay. I see. No, not to search, the graph construction cost. Yeah. So good question. So the main cost is, each of the n nodes has to decide its out neighbors. So that first n is unavoidable. Now the out neighbor step here, this deciding the out neighbors here is a n squared algorithm, because for each edge you have to see what future edges it can block, right? That's an n square step. So what we do is, instead of scanning all the n-1 other points and running this procedure, we have a heuristic to figure out a much smaller subset of important edges, and then only do this procedure on those important edges. What is the heuristic? So it's a good question. So we search path is what we run this prune procedure on. That narrows things down much more. Yeah, it's possible. We haven't done any of those optimizations. The condition for when to not add an edge looks at Euclidean distances. Correct. But now when I told you how to decide what candidates, the entire algorithm I have told you. So there's nothing is hidden under there.
People take sphere pattern, right? All the points which fall upon sphere, I'll just pick ground as my edge. I don't know if this would be faster or slow. That's what essentially doing, right?
Right.
Just make sure that locally
Exactly. Sphere packing at various scales, radius scales. Yeah.
Yeah, that is true.
Yeah. Some sort of it automatically relativizes across the scale. Like each edge will figure out based on its radius what the sphere to.
Big spheres and small
Correct.
small spheres that complete and
Correct.
spheres.
Right.
But I think you can have still here there is a ways in which you're moving to bigger.
No, I mean how to build a graph is a very nice topic to think about. Like we have a heuristic, we have something that works, but it's not clear if that you can do better, can't do better.
How do you actually find the nearest neighbors to the query? You talk about going from one node to the other, but
No, this, right? So this is the algorithm. So you run this greedy type of decentralized routing like this. So if the query is here, you start from your start node, you scan the edges of each of the start node. So start node in this case has like 4 edges, right? You pick the one neighbor who's closest to the query. So you will go to P6. P6 will scan its 4 nodes and it will find out P7. P7 will scan its 4 nodes and nobody is closer than itself. It will stop there.
but then how do you start? Where do you start?
We always start at some like fixed start node. Yeah.
You just continue that, find as
Right.
many
Yeah, I mean, it's true. Yeah, but our experiments show that within 1 or 2 hops you. Yeah. Correct. Correct.
On the construction, you say you have to look at who the neighbors are.
Correct.
Pick one.
Correct.
So the V1 to V7 which are closest is a tough find.
This is actually not the closest, and this is just a toy example where the entire data set has only 8 points. What we do is we run this theory for this to conceptually to make sense, we have to run it on all the n-1 points. Instead, we narrow down a subset of points which we run it on. And the subset is identified by running a search for this point in the current graph. All the nodes that got visited in the search path, they are the ones who we run this procedure on. Somehow from the start till convergence, some nodes were visited in the search path. We just try to add edges to those cases because in the direction, right? It's sort of like linearizing the search space.
So if you incrementally update the points in such a
Yes.
still retains.
No, good question. We in production we rebuild the graph every day, every 2 days. Inserts are fine, deletes are hard. We have heuristics, but not clear if they are the right thing to do. If a node is deleted, we just like cross connect all its in neighbors to the out neighbors and then run this sort of a procedure again on those fellows. But it's not clear if things are all as good as just. Maybe every week, I'm not sure. I mean, these are also things I don't know. I don't even know if I should be saying out, but yeah, yeah. So let's erase everything I said. So. No, so we wrote the code, and people have taken our code and built stuff on top of it to use this. But the code is very simple to implement. It's not very complicated.
Quite a while ago for the distributed hash table. Is that at all relevant to this?
Good question. It's definitely relevant in that another popular approach for nearest neighbor search is to go through hashing, like locality sensitive hashing. So it's a very common way that people do nearest neighbor search in. Our experiments show that this sort of a graph-based thing converges much faster and can achieve the same quality while doing much less work. So we went with this route. One could ask, can you implement this graph search using a distributed hash table for extremely large scale? So those are engineering aspects that one could ask. The other connection I see is LSH, which is an entirely different approach, but maybe that can give us a good start point for the search. For example, use a hash table and find out a start point. It's all possible.
This algorithm computes and run beginning to parallel.
Correct.
Without
Correct. That is highly parallelizable. Okay.
Thank you,
Thanks
Dr.
a lot.
Krishnaswamy, for accepting our request, coming here and delivering such an interesting talk. Thank you, everyone, for attending. We have arranged refreshments in the coffee hut. Please continue your conversations there.
Thank you.